Morning, all. We are studying Laplace transforms, and what I want to cover today is section 8.4. Which is on the unit step function. And this comes up when we are dealing with non-homogeneous differential equations. The simplest are the differential equations where we have constant coefficients on the left-hand side, ay double prime plus by prime plus cy equals some function f of t, and we have initial conditions. Y at 0 is k naught, and y prime at 0 is some k1. And we have what is called the forcing function. That's just terminology. F of t. And in the previous section, we dealt with the case where f of t was continuous. But now we want to consider forcing functions that are piecewise continuous. So a function that is piecewise continuous, let's say on the interval from a to b, might look like this, goes up. And then we have at this point what is called a jump discontinuity. Discontinuity. So we have a function which is continuous, certainly on the interval, the open interval from a to c, and on the open interval from c to b, but at the point c, it's not continuous. There's this jump. So you might have a limit as you approach c from the left and a limit as you approach c from the right, but those two limits are different. That's what's called a jump discontinuity. And a function is piecewise continuous on an interval if it has a finite number of discontinuities. So you might have a function which looks like this. So in this case, this is, say, the interval from a to b. And at these several points, say x1, x2, x3, x4, this function has a jump discontinuity at 4 different points. Okay. So we want to try to solve a differential equation, second order non-homogeneous differential equation, constant coefficients on the left-hand side, but on the right-hand side, the function is only piecewise continuous. We don't know if it's not necessarily continuous. And we do this because in applications, in real applications, in engineering and physics and so forth, equations like this come up naturally. And we're trying to solve equations using the Laplace transform. So we need to figure out, how do you find the Laplace transform of a function with a jump discontinuity? So let's start with an example. By the way, what is the simplest function with a jump discontinuity? There's the function that's called u of t, which is defined to be 0 for t less than 0 and 1 for t greater than or equal to 0. So on the line, this function looks like this. It's 0 until you get to 0, and then it's 1, and it's 1 thereafter. And if you take a number tau and you translate this function by tau, so you look at t minus tau, tau is some fixed number. This is going to be 0 if t is less than tau, and 1 if t is greater than or equal to tau. So for this function, let's say here is tau, this function is 0 until you get to tau, and then it's 1 for t greater than or equal to tau. So, and this is really the most important function with a jump discontinuity for us, right? I mean, this function is continuous everywhere except at the number tau, because the constant function 0 is continuous and the constant function 1 is continuous. But when you get to tau, you jump. This is a jump discontinuity. Okay. So any questions about this function? This is really a key function in a lot of mathematics. Okay. So let's look at an example of a function with a jump discontinuity. Suppose we take the function f of t, which is defined as follows. It's 2t plus 1 for 0 less than or equal to t strictly less than 2, and it's equal to 3t for t greater than or equal to 2. So let's look at the graph of this function. Notice when you're taking a Laplace transform, you need functions that are defined from 0 to infinity, right? Because the Laplace transform, L of f, is an integral from 0 to infinity, e to the minus st f of t dt. Doesn't matter what the function looks like for negative values of t. The Laplace transform only looks at the positive, the non-negative values. So for this function, what does the graph look like? So from 0 to 2, this is the function 2t plus 1. So it has y-intercept 1 and slope 2. So when t is 1, it's equal to 3, and when t is 2, it's equal to 5. So actually, let me draw this a little bit better. So this is 0, 2, 4, 2, 4, 6, 8. So, and f of t is 2t plus 1 from 0 to 2. So this goes from 1 up to 5. And at t equal to 2, it has the value 6. And when t equals 3, it has the value 9. And it goes up a little bit faster. So here we have our one jump discontinuity. Okay. So this function is increasing linearly from 0 to 2, but when it gets to 2, it jumps, and again, it increases linearly, but with the difference, aligned with a different slope. This is slope 2, this is slope 3, and so forth. Okay, so that's the graph of this function, right? That's my function. So how do we compute the Laplace transform? So this function has two different definitions depending on whether you're between 0 and 2 or from 2 to infinity. So I want to write this, I have to write this as a sum of two integrals. The integral from 0 to 2, when t is between 0 and 2, e to the minus st, f of t is 2t plus 1 dt. And then from 2 to infinity, this integral, the function is 3t dt. So we have to compute both of these things. Now, there are many, many ways to do it using just freshman calculus, first year calculus. But since we're studying Laplace transforms, one way to do it, it's not necessarily the best way or the only way, it is simply one way, is to somehow convert this into Laplace transforms. So this is almost a Laplace transform. The only difference is we're going from 2 to infinity and not 0 to infinity. So I can write this as follows: the integral from 0 to 2, e to the minus st, 2t plus 1 dt. And if I want to make this an integral from 0 to infinity, I can. The only thing is I've added here the integral from 0 to 2, so I have to subtract the integral from 0 to 2 of this. So my Laplace transform is equal to this. Let me write this down again. So my Laplace transform is equal to this, the integral from 0 to infinity, e to the minus st, 3, I can take the 3 outside, t dt, and then I have these two integrals. And they're both integrals plus the integral from 0 to 2 e to the minus st, 2t plus 1 minus 3t dt, which is 3 times the integral from 0 to infinity, e to the minus 3t, t dt, 2t plus 1 minus 3t, this is e to the minus st, 1 minus t dt, evaluated from 0 to 2. Now, I can do this in several different ways, and maybe I'll do it in 2 ways. One is, we know this, sorry, this is an S. This is the Laplace transform of t. And we know the Laplace transform of t is 1 over s squared. So this is 3 times 1 over s squared. And this is just an ordinary integral from calculus. You can solve this integral by integration by parts. Let's try and do that. Integration by parts. So I have one part is 1 minus t, e to the minus st. If I differentiate this with respect to t, I get minus 1. If I integrate this with respect to t, I get minus 1 over s, e to the minus st. So the integral from 0 to 2, e to the minus st, 1 minus t dt, is minus 1 over s, e to the minus st, 1 minus t, evaluated from t equals 0 to t equal 2, minus the integral of this, minus times minus is plus, 1 over s, e to the minus st dt, from 0 to 2. So let's see, if I evaluate this at 2, I get minus 1 over s, e to the minus 2s, 1 minus 2 is minus 1, makes this a plus, minus this evaluated at 0. When you evaluate this at 0, e to the 0 is 1, 1 minus 0 is 1, I get minus 1 over s. And this integral, minus 1 over s, What is the integral of e to the minus st? Again, it's minus 1 over s e to the minus st, evaluated from t equals 0 to 2. So I get, let's see, 1 over s e to the minus 2s plus 1 over s plus, I have 1 over s squared, s times s is s squared, e to the minus 2s minus 1. So this is 1 over s plus 1 over s squared e to the minus 2s plus 1 over s minus 1 over s squared. So this is what I put in over here. I have 3 over s squared plus this integral. This integral is 1 over s minus 1 over s squared plus 1 over s plus 1 over s squared e to the minus 2s. 3 minus 1 is 2. So this is 2 over s squared plus 1 over s plus e to the minus 2s times 1 over s squared plus 1 over s. And that is the Laplace transform of this function, which is piecewise continuous. Okay. So again, this is always hard to follow, but that's why the lecture is recorded, and you can follow this on YouTube if you wish. There's an alternative way to do this integral, which is what you find in the text, and it's equally good. So let me do it that way as well. Again, my Laplace transform of this piecewise continuous function f. This is the integral from 0 to 2 e to the st 2t plus 1 dt plus the integral from 2 to infinity e to the minus st 3t dt. And we can convert both of these integrals, if we wish, into a Laplace transform. So if I extend this integral to infinity, this would be the integral from 0 to infinity e to the st 2t plus 1 dt minus the integral from 2 to infinity e to the st 2t plus 1 dt, right? Because if I go from 0 to 2 and then 2 to infinity, I have the integral from 0 to infinity. So that's what this first integral is. Plus this, the integral from 2 to infinity e to the minus st 3t dt. So this is this first integral, 0 to infinity e to the minus st 2t plus 1 dt. And here I have the integral from 2 to infinity e to the minus st 3t minus 2t plus 1. And just note, 3t minus 2t plus 1 is t minus 1. So t minus 1 dt. And so let me just repeat. But this, of course, this is just the Laplace transform of 2t plus 1. And in this integral, if I replace t, if I just change the variables, if I let x equal t minus 2, then as t goes from 2 to infinity, x goes from 0 to infinity. So I get an integral from 0 to infinity with respect to x. If x is t minus 2, t is x plus 2. So this is e to the minus s, x plus 2. And if t is x plus 2, t minus 1 is x plus 1. X plus 1 dt. So except for this 2, but of course, e to the minus s, x plus 2 is e to the minus sx, e to the minus 2s. So I have, this is the Laplace transform of 2t plus 1 plus e to the minus 2s times the integral from 0 to infinity, e to the minus sx, x plus 1 dx. And of course, it doesn't matter what variable I use. If I don't like the letter x, I can just make it t again. Same thing. So this is equal to the Laplace transform of 2t plus 1 plus e to the minus 2s, the Laplace transform of t plus 1. And I know what these Laplace transforms are. This is 2 times the Laplace transform of t. Laplace transform of t is 1 over s squared. So that's 2 over s squared. Laplace transform of 1 is 1 over s. E to the minus 2s. Again, the Laplace transform of t is 1 over s squared, and the Laplace transform of 1 is 1 over s. So we get this answer. And if we compare it to the answer we got when we did the problem a slightly different way, same thing, which is, oops, almost the same thing. I have a minus 1 over s squared. Why don't I have a minus 1 over s squared here? T minus 1, this is x minus 1, minus 1. Minus 1 over s. No, I was right the first time. Yeah, t minus 1 is x plus 1. Plus, this is correct. Huh. Here I got a minus sign. Oh, sorry, this is the right answer. Yeah, that's what I got as the answer. Right, that's exactly correct. Good. So we did the problem in 2 completely different ways, but we got exactly the same answer. That's always a good sign. And the second method is the one you'll find in the book, so it's easy to follow at home. So now let's find a somewhat more systematic way to describe or to write down explicitly piecewise continuous functions. And again, I want to recall the unit step function, u of t. And if you translate this by tau, u of t minus tau that's the function whose graph looks like this. It's 0 until you get to tau, and then it jumps, and it's 1 for all t greater than or equal to tau. So that is the unit step function. And suppose we have a piecewise continuous function, f of t, which has a jump discontinuity at t1. So for t between 0 and t1, it's equal to some function f naught of t. And for t greater than or equal to t1, it's a different function, f1 of t. And I want to write this without breaking it up into two separate pieces like this in sort of one line. So you have to be a little bit clever, or someone at one point was a little bit clever and made the following observation. F of t can be equal to f naught of t. Just one second, excuse me. Sorry. So f naught of t, but I want it to be f1 of t once you hit tau. So let's say it's u of t minus tau, and then it's f1 of t minus f naught of t. So let's look at this expression. What is this equal to? If t, well, let me do it here. This is going to be equal to what? If t is between 0 and tau, this is f naught of t. If t is less than tau, this is 0 plus 0, which is f naught of t. But if t is greater than or equal to tau, this is f naught of t. Then this unit function is 1 times f1 of t minus f naught of t. And then you see that f naught of t and minus f naught of t cancel, and we're just equal to f1 of t. So what we have here is a way to write f of t in one line, if you like. It's one simple expression using, in a clever way, the unit step function. So you need to look at this for a minute and convince yourself that this is really legit, and that is, yeah. Any questions about this? Because this is in some sense very elementary, but it is also fundamental. Suppose we want to just calculate the Laplace transform of the unit step function. That's a good start. So if we have the function u of t, which is 0 for t less than tau and 1 for t greater than or equal to tau, this is u of t minus tau. The Laplace transform of u of t minus tau is the integral from 0 to infinity, e to the minus st, u of t minus tau, dt. But this is 0 when t is less than tau. And for t greater than tau, this is just 1. So this Laplace transform is the integral of e to the minus st from tau to infinity. And again, we make a change of variable if we let x equal t minus tau, or t equal x plus tau. When we change variables, this becomes the integral e to the minus s x plus tau dx from 0 to infinity, which is e to the minus s tau, the integral from 0, sorry, e to the minus x, e to the minus s tau, integral from 0 to infinity, e to the minus sx dx. This is e to the minus s tau times the Laplace transform of 1, which is 1 over s. So this is just 1 over s e to the minus st. So that very nice expression is the Laplace transform of u. So there's a general theorem. So this is the main theorem in this section. Theorem 8.4.1, which says the following. Suppose we have a function g defined from 0 to infinity. Suppose we have a number tau greater than or equal to 0. And if we take the shifted function g of t plus tau, the Laplace transform of this exists for all s greater than some s naught. In that case, if we take the Laplace transform of u of t minus tau, g of t, that's going to equal e to the minus s tau times the Laplace transform of g of t plus tau. So that looks a little bit complicated. Let's look at a simple example. Suppose we take g of t just to be equal to 1. So this formula says the Laplace transform of u of t minus tau is e to the minus s tau. Laplace transform, what is g of t plus tau? Well, if g is the constant function 1, when you translate it, it still is the constant function 1. And the Laplace transform of 1 is 1 over s e to the minus s tau. So a very special case of this result is the Laplace transform we calculated a moment ago. And the proof of this theorem is very nice and is straightforward, but maybe because life is short and the number of lectures left in the course is few, I'm just going to, I won't prove this. The proof is in the text on page 423, and it only takes a couple of lines, but you have to think about each of the lines. Let's just look at the use of this theorem. So here's the first example. Let's take another example. Suppose we take the function g of t to be t squared plus 1, and we choose the number tau to be equal to 1. So what is g of t plus tau? That's g of t plus 1. When you replace t by t plus 1, you get t plus 1 squared plus 1, which is t squared plus 2t plus 2. So our theorem says that the Laplace transform of u of t minus 1 times t squared plus 1, right? That's g of t. It's e to the minus s tau. Tau is 1, so that's e to the minus s. The Laplace transform of t squared plus 2t plus 2. And we know how to compute this Laplace transform. This is e to the minus s. Laplace transform of 2t squared is 2 over s cubed. The Laplace transform of t is 1 over s. Sorry, 1 over s squared. And the Laplace transform of 2 is 1 over s. So that's the answer. That's the Laplace transform. Now, let me show how to use the unit step function and this theorem to compute the Laplace transform of a step function. Let's take the step function that we calculated a moment ago. Let's see. What was that? We had the function defined as follows. F of t was equal to 2t plus 1 for t less than 2, and 3t for t greater than or equal to 2. And we calculated the Laplace transform of f. What we got was 2 over s squared plus 1 over s plus e to the minus 2s, 1 over s squared plus 1 over s. So this is the calculation that we did, and let's try to do it again in a different way using the unit step function. So we can write f of t as equal to 2t plus 1 plus u of t minus 2 times 2t plus 1 minus 3t. Because when t is less than 2, this is 0, and we just get 2t plus 1. And when t is greater than or equal to 2, this is 1. I'm sorry, this should be, I wrote this down backwards. 3t minus 2t plus 1. When t is greater than or equal to 2, this is 1. 2t plus 1 minus 2t plus 1 cancel. We just are left with 3t. So this is equal to 2t plus 1 plus u of t minus t times t minus 1. So the Laplace transform of f is the Laplace transform of 2t plus 1 plus the Laplace transform of u of t minus 2 times t minus 1. Yeah. Laplace transform of u of t minus 2 times t minus 1. Laplace transform of 2 over t, 2t, is 2 over s squared. Laplace transform of 1 is 1 over s. What is the Laplace transform of u of t minus 2 times t minus 1? By the theorem, this is equal to e to the minus s times tau. Tau is 2, so minus 2s times the Laplace transform of t minus 1. So that's 2 over s squared plus 1 over s plus e to the minus 2s. And what is the Laplace transform of t minus 1? It's 1 over s squared minus 1 over s. Oops. Sorry. 3t minus 2t plus 1 is t minus 1. Yep. I just have a minus sign off somewhere, so I need to get this correct. F of t is 2t plus 1 plus u of t minus 2, t minus 1. So the Laplace transform is the Laplace transform of 2t plus 1 plus the Laplace transform of u of t minus 2 times t minus 1. And so u of t minus 2, yes, it's t minus 1 plus tau. Tau is 2 plus 1. That's what I wanted. Times, so this is 1 over s squared plus 1 over s. And that's what we got. So this and this, they're the same. Okay, let's do one more. I mean, these are all complicated problems, but when you get to advanced mathematics classes, you have to learn how to do advanced problems. So let's do one using some trig functions. That's kind of interesting. So let's start with the following function. This function is going to have two jump discontinuities. It's equal to sine t for t from 0 up to pi over 2, cosine t minus 3 sine t for t between pi over 2 and pi. And for t greater than or equal to pi, it's 3 cosine t. So if you look at the graph of this function, what does this function look like? So from -3 to 3, and pi over 2, pi, 3 pi over 2. So from 0 to pi over 2, it's just the ordinary sine function. Looks like that. When t is pi over 2, this is 0 and this is -3. So it jumps to -3. And when t is pi, cosine pi is -1. And if you go from pi over 2 to pi, sine t is decreasing. So this is getting bigger. So this is increasing from 0 to pi, and at pi, it's equal to -1. And once you are greater than or equal to pi, it's 3 times the cosine. So cosine pi is -1, so 3 times the cosine is -3. And now we just have the cosine forever, right? That's what the graph of this function looks like. We have a jump discontinuity at pi over 2 and a jump discontinuity at pi. So the first step is to try to write this function in terms of the unit step function. So f of t is equal to, let's say it's equal to sine t. But then between pi over 2 and pi, so if I look at u of t minus pi over 2, this is going to be 0 for t less than pi over 2. But for t greater than or equal to pi over 2, this is 1. So I can have this as cosine of t minus 3 sine t minus sine t. So when t is between pi over 2 and pi, this is 1. And this and this cancel. I get cosine t minus 3 sine t. And when t is bigger than pi, so u of t minus pi, so for t less than pi, this is 0. But when I get to u of t minus pi, I want 3 cosine t, and I want to subtract off everything else, because when t is greater than or equal to pi, these are both 1. So I want to subtract off sine t minus cosine t, this is minus 4 sine t, plus 4 sine t. And minus sine t plus 4 sine t, I can just write that as plus 3 sine t. So when t is greater than or equal to pi, this is equal to sine t plus cosine t minus 4 sine t, which is cosine t minus 3 sine t. Cosine t minus 3, I cancels this, and I'm left with 3 cosine t. So this is a correct statement. And the Laplace transform of f is then the Laplace transform of this, which by the linearity of the Laplace transform, I can write as the Laplace transform of sine of t plus the Laplace transform of u of t minus pi over 2 times cosine t minus 4 sine t plus the Laplace transform of u of t minus pi times the function, and see 3 cosine minus cosine, that's 2 cosine t plus 3 sine t. So I have the Laplace transform of sine t, Laplace transform of t minus u of t minus pi over 2, cosine t minus 4 sine t, and the Laplace transform of u to the t minus pi times 2 cosine t plus 3 sine t. Now, if I look at my table of Laplace transforms, just make a note over here. The Laplace transform of the sine of t, or the sine of omega times t for any omega, is omega over s squared plus omega squared. And the Laplace transform of cosine of omega t is s over s squared plus omega squared. So the Laplace transform of sine t, omega equal 1, this is 1 over s squared plus 1. That's straightforward enough. The Laplace transform of u of t minus pi over 2. Let's see, where did I write down our theorem? This was the theorem. L of Laplace transform of u of t minus tau, I get a factor of e to the minus s tau. So here I have u of t minus pi over 2. I'm going to get a factor of e to the minus s pi over 2 times the Laplace transform of t replaced by t plus pi over 2. So I have Laplace transform of the cosine of t plus pi over 2 minus 4 times the sine of t plus pi over 2. I need the Laplace transform of that. And here I have u of t minus pi. So I'm going to get e to the minus s pi, Laplace transform of 2 cosine of t plus pi plus 3 times the sine of t plus pi. So this is what we have to evaluate. So let me just write this down again. So I'm interested in the Laplace transform of my function f. It's equal to 1 over s squared plus 1 plus the Laplace transform of this. So this is e to the minus s pi over 2 times the Laplace transform of the cosine of t plus pi over 2 minus 4 times the sine of t plus pi over 2 plus e to the minus s pi, Laplace transform of 2 times the cosine of t plus pi plus 3 times the sine of t plus pi. So this is what we need to compute. Now, cosine of t plus pi and sine of t plus pi are easily calculated in any one of several ways. First, you might remember the addition formulas for the sine and the cosine. So we have the sine of the sum of two angles, A plus B, is sine A cosine B plus cosine A sine B. So in particular, the sine of t plus pi, if A is t and B is pi, is sine t cosine pi plus cosine t sine pi. Sine of pi is 0 and cosine of pi is -1. So this is minus sine t. And the cosine of the sum of two angles is the product of the cosines minus the product of the sines. So the cosine of t plus pi, that A equal t and B equal pi, is cosine t cosine pi minus sine t sine pi. Again, sine pi is 0, cosine pi is -1. So this is minus cosine of t. So this expression, we have L of f, is 1 over s squared plus 1 plus e to the minus s pi, Laplace transform of 2 times the cosine minus 2 cosine t and 3 times the sine minus 3 sine of t. Is 1 over s squared plus 1 e to the minus, I'll write it pi s, the Laplace transform of the cosine. We saw that a moment ago. That's, I'll put a minus sign in front because I have minuses here, minus 2s over s squared plus 1 plus 3 times 1 over s squared plus 1. So this is equal to that's this term here. I forgot, I have to also look at this term. So let me just cross that out for a second. So from what I just calculated, let me just repeat it. 2 times the cosine of t plus pi plus 3 times the sine of t plus pi is minus 2 cosine t minus 3 sine t. So the Laplace transform of minus 2 cosine t minus 3 sine t is minus 2s over s squared plus 1 minus 3 over s squared plus 1. But we also have cosine of t plus pi over 2 minus 4 sine of t plus pi over 2. So if we apply our sum formula, the cosine of t plus pi over 2 is cosine t cosine pi over 2 minus sine t sine of pi over 2. Cosine of pi over 2 is 0 and sine of pi over 2 is 1. So this is minus sine t. And the sine of t plus pi over 2 is sine t cosine pi over 2 plus cosine t sine of pi over 2. Again, this is 0. This is 1. This is just cosine t. So the Laplace transform of the cosine of t plus pi over 2 minus 4 times the sine of t plus pi over 2 is the same as the Laplace transform of minus sine t minus 4 cosine t. And the Laplace transform of the sine of t is minus 1 over s squared plus 1. And the Laplace transform of the cosine of t is s over s squared plus 1. So this is equal to minus, if you like, 4s plus 1 over s squared plus 1. For the first term, this was equal to minus 2s plus 3 over s squared plus 1. So if we take these two expressions and put it into our original expression for L of f is equal to 1 over s squared plus 1 plus e to the minus pi s over 2. This Laplace transform, we just calculated it, is minus 4, make this a minus sign, minus 4s plus 1 over s squared plus 1. And this Laplace transform, e to the minus pi s, we calculated that and got another minus 2s plus 3 over s squared plus 1. So at the end of the day, doing a lot of work, this is our answer. 1 over s squared plus 1 minus 4s plus 1 over s squared plus 1, 2s plus 3 over s squared plus 1. And again, this is the kind of thing, this is hard work. So you need to follow this carefully, and this example is done by essentially this method on page 425 in the text. You need to follow that. Okay. Whew. All right. Sometimes you have to work. So remember, the first theorem, 8.4.1, said the following. Let's see where it is. Yep. Says the Laplace transform of u of t minus tau, g of t, is equal to e to the minus s tau, Laplace transform of G translated to the left by tau. And slight variation of that is theorem 8.4.2, which says the following: the Laplace transform of U of t minus tau G of t minus tau is equal to e to the minus s tau, Laplace transform of G of t. It's just replacing t by t minus tau here. So it's essentially the same thing. And we use this often to find inverse Laplace transforms. Let's look at this. Suppose I have the function e to the minus 2s over s squared. And I want the inverse Laplace transform of this. So I want to find a function of t whose Laplace transform gives us this. Now we know the inverse Laplace transform of 1 over s squared is t. And we know from this, well, we have this formula. In this formula, let's just look at this formula. Suppose I let tau equal to 2. By that tau equal 2 in this formula, it says the Laplace transform of U of t minus 2, G of t minus 2, is equal to e to the minus s tau, e to the minus 2s, Laplace transform of G of t. And suppose the Laplace transform of G of t is 1 over s squared. That is, suppose G of t were equal to t. Well, that's exactly what I have here, right? So if I let G of t equal t, the Laplace transform of G of t is 1 over s squared. So the Laplace transform of this is e to the minus 2s over s squared, which means the inverse Laplace transform of e to the minus 2s over s squared is the Laplace transform is u of t minus 2, G of t minus 2 is t minus 2. And I solved my problem. The inverse Laplace transform of this is u of t minus 2 times t minus 2. What does the graph of this thing look like? If t is less than 2, this is 0. And when t is greater than or equal to 2, this is 1. And this is just the line t minus 2. So this function has a graph, which is this function, which is actually has no discontinuity. It's a continuous function, but it doesn't have a derivative at this point. That's the inverse Laplace transform. Let's try and do some more inverse Laplace transforms. So let me just follow some of the examples in the book to make it easier when you're studying, and when you do the homework problems, you'll deal with things you have to do yourself. Suppose the Laplace transform of some function h is a function capital H of s, which is 1 over s squared minus e to the minus s times 1 over s squared plus 2 over s plus e to the minus 4s over s cubed plus 1 over s. And we want to find h. What is h? Well, if the Laplace transform of h is this, h is the inverse Laplace transform of this expression. And Laplace transforms and inverse Laplace transforms are linear. This is the inverse Laplace transform of 1 over s squared minus the inverse Laplace transform of e to the minus s, 1 over s squared plus 2 over s, plus the inverse Laplace transform of e to the minus 4s, 4 over s cubed plus 1 over s. Of course, this we know, the inverse Laplace transform of 1 over s squared is just 1 over t. But what about these? Let's calculate these separately. So the inverse Laplace transform of e to the minus s, 1 over s squared plus 2 over s, so let's recall the general formula. The Laplace transform, I have e to the minus st, Laplace transform of g of t, is equal to the Laplace transform, and this is tau, of u of t minus tau, g of t minus tau. So the inverse Laplace transform of something which looks like e to the minus s tau, Laplace transform of g of t, is equal to u of t minus tau, g of t minus tau. Now in this expression, I have tau is equal to 1. This is e to the minus 1 times s. And g of t is a function where the Laplace transform of g of t is 1 over s squared plus 2 over s, which means g, if the Laplace transform of g is this, the inverse Laplace transform gives me that g of t is equal to Laplace transform of t is 1 over s squared, the Laplace transform of 1 is 2 over s, t plus 2. And g of t minus 1 is going to be t minus 1 plus 2, or t plus 1. So the inverse Laplace transform of this function is going to be u of t minus 1 times t plus 1. Oops. Is that right? Yeah, t plus 1. What about this function? We want to find the inverse Laplace transform of e to the minus 4s, 4 over s cubed, plus 1 over s. So this is of the form e to the minus s tau, where tau is equal to 4, and the Laplace transform of g is 4 over s cubed plus 1 over s. But what's the inverse Laplace transform of 1 over s cubed? Well, we know that the Laplace transform of t squared is 2 over s cubed. So the Laplace transform of 2t squared is 4 over s cubed. So g is equal to 2t squared, inverse Laplace transform of 1 over s is 1. 2t squared plus 1. So we get our function h is 1 over t minus this, which is minus u of t minus 1 times t plus 1, plus this, which is u of t minus 4 times 2t squared plus 1. Sorry, this is g of t. G of t is 2t squared plus 1. So g of t plus 4 is 2 times t plus 4 squared plus 1. That's 2t squared plus 32t plus 16 times 2 is 32 plus 1 plus 33. T squared plus 8 times plus 16t plus 33. Oh, sorry, t minus 4. This makes this a minus sign. Oh, okay. Really, the best thing to do is to spend a lot of time over the weekend learning this technique of Laplace transforms and inverse Laplace transforms of functions multiplied by a unit step function. And on Monday, we'll learn how to put this all together to solve a differential equation where the forcing function is a piecewise continuous function. That's what's left for us to do. Okay. All right. A lot of work. Interesting, though. Any questions before we quit for the morning? If not, then I wish you all a pleasant day and see you on Monday. Bye.